This is an example from section 5.4 on gravity and orbits. So we have a satellite circling the Earth, 780 kilometers above the Earth, and we are trying to find out the speed of the shuttle that released the satellite. In other words, the speed of the satellite that allows it to be in uniform circular motion at that height above the surface of the Earth. So the governing equations here is Newton's second law, where F net equals MAC, where AC is the centripetal acceleration. And for uniform circular motion, F net is all the forces that point toward the center of the circle minus the forces that point away from the center of the circle, of which in this case there are none. So we have the Earth, and then out here we have the satellite. It is the satellite that's in the uniform circular motion. Okay. Now the important thing to remember about this circular motion is you must measure the radius of the circle from the center of the Earth out to the satellite. So that is the little r. And we are given the altitude of the satellite, which we'll call h. Okay, so you always have to remember where RE is the radius of the Earth, that the radius of the full circle is the radius of the Earth plus the height above the surface of the Earth. Okay, now the force that is pulling the satellite towards the center of the circle that keeps it in the circular orbit so it doesn't fly off into outer space is the force of gravity. And so our net force in this case is simply the force of gravity between that satellite and the Earth. And we have covered this before. It is G, mass of the Earth, mass of the satellite, over the distance between the centers of those two objects. Now we're going to assume the satellite is so small compared to the Earth that the distance from the surface of the satellite to its center is negligible. Okay, so there's our net force. The acceleration we've also done previously is v squared over r. And so when we put that together, we get that the force of gravity is equal to mv squared over r. And the force of gravity is g m over r squared. Now you have to be careful which mass is which here. The object going in the circle is the satellite. So this mass is the same as this mass, and those masses cancel. So it really doesn't matter what the mass of that satellite is, it's going to have a particular speed given its distance from the center of the Earth. And every single particle, whether it's a speck of dust or a huge satellite or a spaceship, must have that speed if it's going to be at that distance from the surface of the Earth. If it's going too slowly or too quickly, it will move away from that orbit. Okay, so the unknown here is speed. So we're trying to find the speed of the satellite. So the physics is done. We're just now ready to do the math. Okay, so we just need to solve that for v. So we get that v squared is equal to g m mass of Earth over r. Notice how one r cancels that r, so we're just left with r. And then the speed is the square root of gm Earth over r. Now, this is a pretty common formula for satellites. Notice how it does not depend on the mass of the satellite. It depends on the mass of the object the satellite is circling. So this is the mass of the Earth, and that's what counts. Okay, and so we'll put the numbers in. G 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Mass of the Earth, you'll be given that, you don't have to memorize that, 5.98 times 10 to the 24 kilograms. And then the distance from center to center, this is all under the square root, is the sum of the radius of the Earth, 6.371 times 10 to the 6 meters. Be careful that that's in meters, not kilometers. That's often written as 6371 kilometers, but it has to be in meters. And then we're going to add the altitude above, once again, in meters. So we have to convert the 780 kilometers to meters, which is 7.8 times 10 to the 5. Okay, put those numbers in your calculator, and you get the speed to be 74.68 meters per second. And that is the answer. They have to go incredibly fast in order to maintain their altitude.